Hello friends. So today we are going to solve four questions, and these four questions are from collision, elastic collision, and we can say conservation of momentum as well as conservation of energy. So the first question, it is asked that a block of mass m moves with initial velocity v0 on a smooth horizontal frictionless table towards a rigid vertical wall. A ball of mass small m, which is very much less than capital M, is initially at rest on the table, positioned at a distance L from the wall, directly in the path of the block. The block undergoes a perfectly elastic collision with the ball. After this collision, the ball moves towards the wall, reflects elastically from it, and subsequently oscillates by repeatedly colliding elastically with the block and the wall. So based on this, we are having two questions. Part A, determine the minimum distance between the block and the wall during this process. And part B, determine the total number of elastic collision between the ball and the block up to the instant the block reaches its point of closest approach to the wall. Okay. So in this case, we are given, we can just draw an approximate figure. Suppose this is the wall, and we have a plane frictionless surface on which we are having a block that is a capital M, and we have a ball whose mass is small m, and this capital M is moving with the velocity of v0 toward the wall. Okay. And the ball is at a distance of L from the wall initially, and at this position this ball is at rest. Okay. So this is our block and this is our ball, and ball is initially at rest. So okay, so in this case we are given that all the collision at all the surfaces are elastic. It means collision between the block and the wall is elastic. A ball is elastic, and the collision between the ball and the wall is also elastic, and all the surfaces are frictionless. Okay, so these are some things which are given to us. So let us discuss the first collision between the block and the ball. First collision between the block and the ball, and for that we are going to take our initial velocities, and we are given, we are going to consider first of all the initial velocities, and we are given that the initial velocity of this block, let us suppose, is our um, that is given to us as v0, and initial velocity of the ball, that is u, this is capital M, and u for this our small m, that is our ball, is equal to 0. Okay. So this is our block and this is our ball. Okay. So there is an elastic collision between the two. So you can say for for the elastic collision, we can write the final velocity equations. So we can say the final velocity of the block velocity for the block, let us suppose that is given as Vm, then this Vm will be equal to capital M minus small m, capital M plus small m multiplied by its initial velocity. And similarly we can write for the ball, and that ball will be our 2m, m plus capital M, and that will be equal to u of capital M. And for ball we write this as a v of small m. Now we are given that our m is very much greater than small m. Therefore we can write that our v of m will be approximately equal to v naught 1 minus 2m divided by capital M. And from here we can further approximate it, and we can write that our Vm is approximately equal to twice of V naught. Okay. So it means, from here we can also say that the velocity of the block is going to slow slightly after each collision. Okay. So we can say that velocity of block will decrease after each collision. This we are going to use later on also. Okay. And so let us consider now the nth collision and try to sort it out, how the velocities and everything is going to change. Okay. So you can say at the nth collision, let us assume that our v of n is the velocity of the block just before the nth collision. Is the velocity of a block just before nth collision. Okay. And ball, we have to remember, is going to elastically bounce from the wall and is moving toward the block, okay, during this nth collision. So we can say under this condition we can write the ball has just bounced elastically from the wall and is moving towards the block, towards the block. So we have to remember that we are saying that this v of n is the velocity just before the nth collision. Okay, so when just before the nth collision, the ball is already in the process to strike the block, so that the collision that is going to take place is our nth collision. And we are given that every collision is elastic collision, and we know that the position of the wall is fixed. Okay, so it means the ball speed is not going to change when it is going to strike the wall. Only the direction will be reversed. Okay, this will be the effect of the ball on the wall. So we can say that because the wall is fixed and sorry, 1 second. Ball on the okay, sorry for that. Okay, so we were discussing that the wall is fixed and the collision is elastic. The collision is elastic. So based on this, we can draw two conclusions. First conclusion is that the ball's speed is unchanged by the wall. And second, we can write that its direction is reversed. It means the direction of the speed of the ball is reversed. So you can see its direction is reversed. It means whenever there is a collision between the ball and the wall, the magnitude is going to remain the same, only the direction is going to be reversed. Okay. And we are given a condition, and that condition is with respect to their mass, which states that capital M mass of the block is very much larger than the mass of the ball. Okay. So based on this also, we can write rather that the block speed changes only slightly, only by small amount during the collision, during successive collisions. Okay. So it means that just before collision, we can write that velocity of our block is our v of n, and for our ball is our minus v of n. Now we can use the momentum conservation during the collision. Momentum conservation, and we here discussed that at the nth collision. Okay, now we are going to discuss n plus 1th collision. Okay. So you can say for n plus 1th collision, let us assume that Vn plus 1 is the block velocity after the collision. After the collision, and we know that the ball is going to reverse its direction in the collision, so we can easily find out its change in the velocity. So we can say the ball reverses direction in the collision. Therefore, its change in velocity let us call this as delta V of m. Then we can say that our delta V of m will be equal to V of n minus of minus V of n, and this gives us twice V of n. And based on this, we can find out the momentum gained by the ball. So we can say momentum gained by the ball, and let us call this a delta P of m. Then we can say that our delta P of m is equal to mass into change in velocity, that is twice V of m. And by conservation of momentum, the block must lose the same amount of the momentum that is gained by the ball. So the momentum gained by the ball is delta Pm. Therefore, the momentum lost by the ball should be also equal to delta Pm. You can say that by momentum conservation, momentum gained by the ball should be equal to the momentum lost by the block, which gives us m v of n plus 1 minus v of n, and that is equal to our minus twice m and v of n. Okay. So we can solve it for our v of n plus 1, and we get from here that v of n plus 1 will be equal to this vn will be our common, so we can take it outside, and we get this as 1 minus twice m upon capital N. And we can also draw one important conclusion, which states that in each collision, the reduction in the speed of the block will be by the same fraction, okay, because the mass and the change in velocity will be over 2m upon capital M. So you can see that each collision reduces the block speed by same fraction, or we can say that the change in speed, its fraction, will be equal to twice m upon capital M. So every time the reduction in the speed will be same. Now this process is going to be reoccurring time and again because there is a n number of collisions between the block as well as the ball. Therefore, we can make a reoccurrence equation. So we can say reoccurrence equation, and so for that we are going to start with the initial velocity, and initial velocity of the block is given as v naught. So you can say initial velocity of the block, which is given to us as v naught, and therefore for next v1 we are going to get this as v naught 1 minus 2m upon capital M, and next velocity is our v2, that will be dependent upon our v1, so this will be coming as v1 1 minus 2m upon capital M, and v1 we already know in terms of v naught. Therefore from here we can write that v2 will be equal to v naught 1 minus twice m upon capital M raised power square. Therefore for nth collision we can write that v of n is equal to v naught 1 minus twice m upon capital M whole raised power n. This is our the equation for our reoccurrence. Okay. Now we can solve this further, and for that we are going to take you can say exponential approximation method, and for that we are going to assume that we have a suppose we have a epsilon, and that is equal to ratio of 2m upon capital M, and which is very much less than 1. Okay, because we are given that our capital M is very much larger than our small m, that condition is given to us. So it means, so we are interested in this part only. So first of all we can write from here that this will be equal to 1 minus epsilon whole raised power n, and our this we know the expansion of the term, and that term is our natural log of 1 minus epsilon, and it is a minus epsilon square upon 2 and minus and so on. So if you consider ignoring the higher terms, or sometimes it is also called as a leading order. Okay. So we can say to leading order we can write that natural log of 1 minus epsilon is equal to approximately minus of epsilon. Therefore we can say 1 minus epsilon whole raised power n is equal to e raised power n natural log of 1 minus epsilon, and this gives us e raised power minus n times epsilon. Okay. So it means we can just solve this equation now. We can write that our v of n, which was our v naught 1 minus twice m raised power n, we can say that approximately equal to v naught e raised power minus 2nm upon capital M. Okay, and this is derived under the condition that our small m is very much less than our capital M. So this is our velocity of or our nth collision for our block. Okay. Now we come to the part B, and part B is our distance of closest approach or closest approach of the block to the wall. So part B, we have to find out the closest approach of the block to the wall. And closest approach means, because we know that after every collision the block is going to reduce its speed only slightly. So at suppose n number of collisions, the block will be coming to a standstill. Its velocity will be equal to 0, and that distance or that instant where the block's velocity comes equal to 0, that will be called as a closest approach distance of the block to the wall. So we can say that the block's velocity comes equal to 0. So this we can say is our closest distance of block to the wall, and let us call this distance our minimum distance, d minimum. Let us call this as minimum distance and define it as our d minimum. And in the you can say we know that every collision is elastic collision, and there is no external force acting anywhere between all these systems, like there is a wall, there is a ball, and there is a block. So there is absence of external force. Okay. So it means the total energy is going to be conserved, or rather we can say total mechanical energy is conserved. So this basic principle we are going to use to find out the distance of closest approach. And we also have to remember that wall only reverses the ball's velocity. So whenever the ball strikes the wall, its velocity is going to, direction is going to change, magnitude is going to remain same. So it means if this is the wall and a ball is traveling, suppose with the velocity of our v, then after striking it will be returning back with the same velocity v with the opposite direction. Okay. For the sake of that, we can just put it as a minus of v. Magnitude will be same, only the direction will be reversed. So we have to keep this in mind. Okay. And total mechanical energy is conserved. So we can say that our total mechanical energy is conserved. It means all the energy lost by the block ultimately will be gained by the ball. Okay, because wall, there is no change with respect to ball with respect to the wall. So we can say that initial energy of the system and in this initial energy of the system, only the block is moving, ball is at the rest, and the wall is permanently fixed. Okay. So we can say initial energy of the system. So we have our block whose mass is given as capital M and its velocity is v naught, and we have a ball whose mass is given as small m and is at rest. So initial energy of the system will be the energy that will be associated with the block only. Therefore you can write that total initial kinetic energy, total initial kinetic energy, let us call this as our EI, will be equal to over half m v naught square. And energy at the moment of the closest approach, the block velocity will be equal to 0. So it means all the kinetic energy will be distributed or transferred to the ball. So you can say that energy at the moment of closest approach we know that block is at rest. Therefore, we can say that the velocity of the block will be equal to 0. So it means by the conservation principle, we can write all kinetic energy is carried by the ball. And at this instant, let us assume that ball's velocity, ball speed at this moment, let us suppose this is V max. Therefore, we can write that total energy at this moment, let us call this as E closest, will be equal to our half m v square max. And we can now apply principle of conservation. So we can say by energy conservation, our initial energy is equal to our E closest. And E closest in other terms we can also call as a final energy, okay, because after that the block is not going to move. So that will be the final energy of a block. So we can also call it a final energy, but that doesn't matter. So we can just substitute it. We get this as half m v naught square is equal to half m v square max. And from here, this half and half goes away, and we get that the maximum velocity of the ball will be equal to v naught and the ratio of capital M to small m. So at the distance of closest approach, the velocity of the ball is our maximum velocity governed by this particular equation. Now we come to our, now we have to relate the velocity to the distance of the closest approach, that is a d minimum. So we have to relating closest distance to velocities, because this is going to help us to find out the d minimum. Okay. And in this case we are going to consider the and we know that as the distance is going to reduce, the velocity is going to increase. Okay, so that's why we wrote here maximum velocity. So it means we have to make a connection or draw a relationship between the distance and velocity growth. because initially the velocity of the ball was 0 and finally it has increased to this value v maximum. It means the velocity of the ball is increasing steadily. Okay, so we have to make a relationship between this distance as well as the velocity growth. Okay. And for that, let us assume that at any moment of time, x is the instantaneous distance between the block and the wall. Instantaneous distance between block and wall. And at this particular moment, we define v as the instantaneous block speed towards the wall. You can say that we have instantaneous block speed toward wall, and at this same instant, let us call this as small v, is the instantaneous ball speed. Ball speed. Okay. So it means the time between two successive block ball collision. Okay, so we are going to find that first of all, and we say time between two successive block wall collision. And for this successive collision, we know that the ball travels to the wall and back. Okay, so it means the distance traveled by the ball will be 2x. So we have assumed, as per this, we say that suppose this is the wall, and at any particular moment this is our block, and the distance between the block and the wall is our x. So it means between two successive collision, the ball should be traveling towards the wall, that is one time x, and then it should be coming back, so that will be 2x. Okay, so the distance traveled with the ball, okay, so this is our ball, will be equal to 2x. Therefore we can say the ball travels to the wall and back. So from here we can say the distance traveled will be equal to 2x, and the ball speed we know is our small v. So from here we can say that the time interval let us suppose is our delta t. This will be equal to total distance divided by its velocity. And now we are going to find out by how much position the block is going to change or travel within this time period delta t. So next, based on this, we are going to find out change in block's position during this time. during this time, because we know as the ball is traveling towards the wall, the block is also continuously moving. Okay, so we have to keep this in mind. Therefore, we can say that so let us suppose that this change in position is given as by delta x block, which will be equal to the velocity of the block and time delta t. So we can say this will be v 2x upon v. Okay. And obviously the block will be moving towards the wall, so this distance is going to decrease, and because of that we are going to put that negative sign. So we can say delta x block will be equal to minus 2v upon v into x, because the distance is decreasing. Okay. Now we can just write it in terms of a differential equation also. So we can say this our second. So we get this as dx upon dn will be equal to minus 2v upon v times x. Okay. So this is a direct conversion into the differential equation. And we also need the relationship between the velocity of the block as well as the velocity of the ball, which is quite easy. We simply use the energy conservation. So we can say energy conservation and the energy conservation, we can write that our half m v square plus half m v square is equal to half m v naught square. So on the right side is initial energy because only block is moving, and the left side we have two velocities, velocity of the block as well as velocity of the ball. And from here we can cancel out this half throughout, and we get that the small v, that the velocity of the block, velocity of the ball will be equal to m upon ratio, and this comes as v naught square minus v square and its square root. Now we can easily replace this velocity in the differential equation, and we get dx upon dn will be equal to minus 2x, and this comes v upon m upon small m and v naught square minus v square and its square root. Okay. And one second. Yeah, we already have it. So we can just make a change of variable. So we can say the change of variable from n to v, and we can write this as our dv upon dn is equal to minus twice m upon capital M times v. And from here we can say that our dn will be equal to, this comes as our m upon twice m minus m upon twice m, and this is dv upon v. Therefore in this equation we can write that our dx upon x will be equal to m upon capital M and square root, and we have this as dv upon v naught square minus v square and its square root. Okay, now we have everything because we have a relationship between our distance and the velocity. So we are just going to integrate it. Okay, and integration, the ball was initially at a distance of L and it travels to a minimum distance of d minimum, and with respect to the velocity, we know that its initial velocity of v naught and final velocity should be equal to 0, because at d minimum it has to stop. And so now it's a quite simple integration. On the left side we are going to get natural log of x, and that is going to give us natural log of d minimum upon L is equal to, and on the right side we are going to get this as minus pi by 2. Okay. And from here we can write that our d minimum upon L is equal to exponential minus pi by 2 square root of m upon